Hello, everyone. Welcome to another lecture for Auto 105 Manual Powertrains. Today, we're going to talk about Chapter 16, which is four-wheel drive theory and operations. We're going to look at not only 4x4 systems, but also all-wheel drive systems, and we're going to discuss the difference between the two. Often that can be kind of misconstrued. A lot of people can think that four-wheel drive system and an all-wheel drive system are the same thing, and they are not. What we're referring to on either one is that more than just one axle shaft will receive power. Now, I want to make it abundantly clear that unless there's locking differentials, it still really is only two-wheel drive because you have one axle driving in, or one wheel driving in the front and one wheel driving in the back. But what four-wheel drive systems allow for is multiple torque to be distributed based off of driver input. All-wheel drive systems, it is computer controlled, does not take driver input. The vehicle is either able to mechanically figure out how it's going to split the torque front and rear, and sometimes left and right, or it's going to be able to do it based off of a computer. Now, there's a couple different four-wheel drive systems that we can have. There is full-time four-wheel drive, and that's where all wheels are powered. Full-time four-wheel drive systems are very similar to an all-wheel drive system, with the caveat that the transfer case can be put into a low range, where all-wheel drive does not have a low range. All-wheel drive simply just powers everything equally, and we don't have an additional gear ratio that we can change that to. Part-time four-wheel drive is what probably most of you are familiar with seeing in like Jeeps and off-road vehicles. Part-time four-wheel drive indicating that part of the time you can drive the vehicle in two-wheel drive, or you can select it to drive in four-wheel drive, depending on the road conditions. So in most driving applications, in fact, about 98% of the time the vehicle is going to be driven, it's going to be driven in two-wheel drive or just rear-wheel drive mode only. And then when we select four-wheel drive, either high or low, it will then send torque to the front wheels. And then there's also on-demand four-wheel drive systems, which are very similar to part-time four-wheel drive systems, with the exception of you can set it into an automatically shifting mode, meaning that you can tell the vehicle, hey, I'm in sand or I'm in mud or I'm going over rocks, and the vehicle will then adjust accordingly so that you have the proper traction and you're not going to get stuck. When it comes down to it, when we look at 4x4 or four-wheel drive, those are systems that are to prevent you from getting stuck when you are off a highway. All-wheel drive systems give you traction in inconsistent driving conditions or give you traction for acceleration. So we want to kind of look at them both a little bit differently there. Now, if we look at a four-wheel drive layout, part-time and full-time four-wheel drive will have similar layouts in that we'll have the engine typically located up front, the transmission right behind it, and then a transfer case or our torque splitting unit after that. And the transfer case is going to be sending torque to the rear differential as well as the front differential. So we'll have two drive shafts, one going forward, one going back. Now, selection can either be done through mechanical levers or through an electronic switch. We're going to have four different options that we can shift into. I want to make sure this is clear. The transfer case is post-transmission. So the transmission, if it's a manual like what's photoed here, you can go first, second, third, fourth, fifth, reverse, and then also then shift the transfer case. So you're going to have the three sticks in this particular application, but quite often you're just going to have one. The twin stick option that we have here in this Jeep is for a high and low range box that goes in between the regular transfer case. But what we'll have is you'll have a two-wheel drive option, which is the most common option that vehicles will be in. I want to make it abundantly clear. Holy Jim Trail is not off-road. It's not going off-road. That is a fire road. Fire road is hard packed dirt. You can drive in that in two-wheel drive. In fact, you can drive almost every fire road until you start to get where you're having to drive through a wash in two-wheel drive. You have to go into four-wheel drive or four high when you're starting to get into very slippery material and you're going at slow speed. That's the key thing there. If you're driving at fast speed, you're not going to be in four-wheel drive, and we'll talk about that here in a second. But four high is the first four-wheel drive selection, and four high is going to have the same ratio or output ratio that two high would have. The difference is we're sending torque to the front wheels as well as the back wheels if it is a rear-wheel drive biased vehicle. The next selection would be neutral. Neutral is what we're going to use to tow the vehicle. So we can have trans neutral, but the transfer case will still be in gear, and that will still turn powertrain components. If we put the transfer case into neutral, then we'll have the ability for everything to freewheel. It's also a good option for you when you're pushing a four-wheel drive, as you put it into neutral. No matter what you do with the transmission or the engine, vehicle's not rolling anywhere. And then the last selection is going to be for low. Now, for low, we'll have an additional torque multiplication low range gear that will increase the output torque of the transfer case. So if we're in first gear, for instance, and we have a 3.5 to 1 ratio, and we shift it into for low, and it's additional 3 to 1 ratio, we're upwards of 11 to 1 ratio before we get to the differentials, and then we're multiplying it again once we get to the diff. You do have the ability, if you have a doubler box where you have a double low range transfer case, where you have a transfer case with a low range box in front of it, you do have the ability to have something like outrageous, like 85 to 1 ratio, where you can effectively get out of the vehicle and the vehicle will just roll on its own. Even if it's a stick shift vehicle, it won't stall because there won't be enough friction based off of the drive wheels for it to stall the vehicle. Now, you're not going to go very fast. You're going to be going less than a mile per hour, but it is an example of what you can have in that type of situation. On modern vehicles, we can have the shift option for auto. That's almost always going to be a button. So anything that's going to have a shift lever that is manually shifted will not have an auto function. And that's because we're going towards a computer controlled transfer case versus a manually controlled transfer case. Our four-wheel drive suspension system is going to vary. A lot of vehicles will have straight axles. A straight axle is very common, especially in the front and the rear. It makes it very robust and strong. We're not super worried about unsprung weight in this situation. The only thing that's a little bit unique with the front axle of a four-wheel drive versus the back axle is A, the ring and pinion are going to be cut backwards so that they could spin the forward direction. And B, we're going to offset the differential to one side or the other. Most of the time, manufacturers are going to have the differential offset towards the left of the vehicle, but we can also have it to the right. Really kind of depends on how the manufacturer has laid out the chassis and which direction the transfer case is going. The transfer case is going to send the torque to the front drive axle if that's the case. A lot of modern vehicles are going to employ independent front suspension. When this is the case, the differential will be fixed to the frame and we will send our power through axle shafts down to each wheel. Now, the axle shaft is going to have to clear the strut and the spring assembly, and oftentimes we see a lot of four-wheel drive vehicles, like what's photoed here with a Chevy Tahoe, is a torsion bar front suspension so that we have clearance. The downside to independent front suspension in regards to four-wheel drive is we won't have as much wheel travel as we would with a live axle front. And the reason for that is we're limited on how much our CV joints or constant velocity joints can allow for the movement of that axle shaft. However, it does allow you to have a much smoother ride, less unsprung weight, so you have better acceleration, better braking. And for most off-road applications where you're not going kind of extreme, it's going to be just fine. Now, our part-time four-wheel drive system, again, is going to be pretty typical. We usually will have some way that we can engage or disengage the front axle so that we can send torque through it. Just because you have the system in four-wheel drive does not necessarily mean you have all four wheels driving, and it's going to be a scenario where you might have to get out and lock hubs. And again, we'll talk about that here in a couple of slides. Now, when we are transferring the engine's torque forward and back, we are having a situation where all four wheels are going to be giving torque equally. Now, going around a corner is going to be problematic for that. When we're going around a corner, we will have the wheels spinning at different ratios. So that's why it's really important when we are off-roading, we are going to be in two-wheel drive if it is firm or going at speed. If we're doing something like what's photoed here with what we're rock crawling, where we're going to be in four low because we're going around obstacles and we're going very slow, then that is going to be fine to be in four-wheel drive. If we start to drive at speed in four-wheel drive, we will get a very aggressive vibration through the chassis. We will also be able to put a lot more strain on the components. The driveline components wear out faster and tires will wear out faster. I have had customers in the past that they get a little bit overzealous with the use of four-wheel drive. I had one customer in particularly that had a 3500 dually truck that he, anytime it was wet at all, like, this, if you woke up this morning and there was like a little bit of, morning dew on the ground, four low, doesn't matter. In his mind, you had to be in four-wheel drive anytime the road surface could possibly be slippery. So he would drive his 3500 four-wheel drive dually pickup truck on the freeway at 80 miles per hour in four low. And that particular truck, transfer case is dumb. It's assuming the driver knows better. It did not care. He literally would go through a set of tires. I'm not joking. All six tires in a dozen miles, and he would bring it into the dealership super upset and pissed off because the tires are wearing out and there's gnarly vibrations through the frame and the truck doesn't drive well. And I would get the vehicle, I'd put it in two-wheel drive and I'd drive it and be like, yeah, it's fine. Like, well, no, in four low, it drives poorly. And I was like, well, here's the deal. You're only supposed to drive in four low. And what I have photoed here, serious off-road, speeds below 2 miles per hour, and in situations where you're trying to avoid getting stuck. He didn't want to hear that. We had to get Chrysler involved, and Chrysler unfortunately ended up voiding his warranty when they found out that he openly admitted, yeah, I'm in four low all the time. I want to have the traction. Now, it actually is making the vehicle more unsafe in that situation. So if we look at the diagram that I have photoed here, when a vehicle maneuvers around a corner, either left or right, it doesn't matter. Each wheel assembly is traveling a different distance, which is going to mean our inside wheels are going to have to travel a shorter distance, especially if we look at the left rear, than our front wheels on the outside. So if we compare our left rear to our right front, we can see a very big difference in the distance that's traveled. If we have it in four low and everything's locked together, that's going to cause either the front tire to bind up and skip because it's slowing down for the slower left rear, or the opposite. It's going to bind and skip the left rear so that we can speed up to the right front. And that will cause the vehicle to hop and buck. That will wear out the tires, wear out the powertrain, wear out the chassis. It's really bad for that to be the case. I cannot stress to you enough. Four high and four low is at speeds below 3 to 4 miles per hour and when you're about to get stuck. So if you can see, you're on a fire road and you're going to cross into some water, you shift to four high if you're going to use some speed to get you through. If you think it's rather deep, you shift it to four low and you kind of, crawl through it really slow. Once you get out of the puddle, you shift it back into two-wheel drive. Again, you're doing less damage and strain on the chassis because of this. Now you'd think like, well, no, I'm going perfectly straight. Even slight altercations to the left or the right, 5-degree steering input is going to cause things to bind up. So you will want to make sure that we are properly using four-wheel drive. And again, I can't stress enough, Holy Jim Trail is not an off-road trail, not even in the slightest. Yes, I know there's a couple things that you can drive up the hill like 2 or 3 feet on either side. It's not off-roading. Uh, Going off on a little bit of a tangent, very good friend of mine. He used to be a editor for Peterson Four Wheel and Off Road, so he would contribute articles and he would do tech stuff. and he built serious four by fours. He had a quad steer, full Detroit locker on 40-inch tires Jeep. And he moved down here from Sacramento, where he was always on the Rubicon Trail or, off-roading around Tahoe. And he got told, oh, hey, man, there's an off-road trail. It's called Holy Jim Trail. We looked it up, did his research beforehand, and saw that it's a fire road. And so he wrote a full article about the difference between off-roading and fire roading. And to prove the point, the other thing that my buddy Nick was really into is he's into scooters. He has a collection of Vespa scooters. So he and his wife took off on a Vespa scooter and drove all the way up to or rode, I should say, all the way up to the top of Saddleback. So he was proving the fact that, no, it's a fire road. You can take a normal car on it. It's just you got to, go slow. So kind of proving the point that there's a difference between off-roading and fire roading. And please make sure you're not wearing out your vehicles unnecessarily. Now let's get into what all-wheel drive is. So all-wheel drive is going to give us the benefit of a four-wheel drive situation. However, it's going to do it automatically. It's going to operate much smoother, and it's going to know when you're steering left or right to unlock the wheels to allow for you to not be binding up the drivetrain and therefore not wear out the tires and have a much smoother application. I can tell you from experience, my daily driver is all-wheel drive, and I cannot tell a difference except for when you accelerate or when you do start to lose traction in the wet. I never have in my station wagon. Now, I used to drive a two-wheel drive Tacoma before that, and any of you that have ever driven a two-wheel drive small pickup truck know that if it gets wet out, it's you're sliding left and right. We always called my truck the D1 Tacoma because it drifts around every corner in the wet. So it is one of those where you want to make sure that you have an understanding of how all this functions. All-wheel drive vehicles are going to be biased either one way or the other, depending on if it's a front-wheel drive primary application or rear-wheel drive application. In the case of my Subaru, it's primarily rear-wheel drive, but it will still send about 40% to 30% torque to the front. Now, all-wheel drive systems are not meant for like rugged, crazy off-roading. Again, this is for low traction type situations. Both four-wheel drive and all-wheel drive systems will have to have some sort of mechanism to split the torque to the front axle and the back axle. On 4x4 or four-wheel drive applications, it's commonly referred to as a transfer case. On all-wheel drive applications, it's either a PTO or power transfer unit or power transfer output. It is going to be a device that will not have any mechanical controls and also will not have a low range. We'll talk about that here in 2 or 3 slides. But our transfer case for a four-wheel drive system is not only going to have a low range gear set in it, but it will also be able to transfer the power, the torque, to the front and to the rear of the vehicle. Our transfer case, for the most part, is going to be bolted to the back of the transmission. In some older applications, especially very early four-wheel drive systems, it can be known as a divorced transfer case. The transfer case actually will have its own drive shaft coming from the back of the transmission to the transfer case, and then one to the rear axle, one to the front. So there'll be 3 drive shafts if that is the case. It's important to know history of four-wheel drives. Manufacturers, the OEM manufacturers, didn't start producing four-wheel drive vehicles until the late 50s into the 60s. So if there was a four-wheel drive vehicle that was out there, it was upfitted. So there's a gentleman that goes to Cars and Coffee quite a bit. It's either a 47 or a 48 Ford Woody, and it is upfitted with a four-wheel drive system. So it's a Mercury Woody that's lifted up, and it's a teal color. It's really nicely done. But that would have been, you would have either sent it after you had purchased the vehicle, or you would have requested after the vehicle was off the assembly line to go to an upfitter where they then install the new front drive axle, the transfer case, and all of the associated running gear that goes along with that. And in that situation, they typically would be a divorced transfer case. But our conventional systems is bolted directly to the back of the transmission. Now, the output shaft will be splined directly to the input of the transfer case. The transfer case can then be constructed from a couple different style designs. We can have either, which is most common, a chain design, which runs a chain between the front input to the rear output and the rear output. We can have it gear driven, which gear driven transfer cases are a little bit older but much stronger. And we can have it also be a band, which band transfer cases were only found in very, very light torque application for four-wheel drive systems. And typically they were all-wheel drive when you actually looked at the construction of them. Our 4x4 systems will utilize a transfer case that will have a low range. Typically, that's going to be through a planetary gear set that will be in front of our input for the transfer case. And that low range will then go through the planetary gear set to increase the output torque of our drive axle. Gear drive transfer cases will be a little bit different to where they will have any type of gear ratio or low in the gear train itself. We often see a lot of these type of gear style transfer cases will have a center differential. And that center differential will be there to assist in that the front and rear will not bind. Toyota Land Cruisers employ these as well as Land Rovers, every version of actual off-road Land Rover, not the little like Equus or whatever, the small front-wheel drive one that's effectively a Ford Focus, but the actual like Land Rovers and Range Rovers and Discoveries, those are going to have this type of transfer case. We'll have a center differential, and any type of low range will be selected via those gears. It has the option to be two-wheel drive, or it has the option to be four-wheel drive. One of the things to note here is the transfer case that's photoed here has both of our drive axles on the right side of the vehicle. So we can have it offset in the front and in the rear. Our transfer cases or our PTOs for all-wheel drive vehicles are going to be a little bit different. A lot of all-wheel drive platforms are going to be based off of a front-wheel drive application. So what we'll have is, instead of having a transfer case that's right after the transfer case will be on one side of the transaxle. So what's photoed here is the transaxle is on the left of the screen. So this is going to be our transaxle right here with our transfer case right here. So what we're doing is we're interrupting the right side axle to send torque through our transfer case and then out through the drive shaft, while also going out to the right side, to where the left side or the driver's side will go straight through. We're usually sending a split of torque, so it's not going to be 100% torque to all four wheels. We can have everything as low as 15 to 1 or 15 to 85 split, up to a 50-50 dependent on the chassis application. There are some weird applications. There is a Ferrari FF out there that does have, instead of a transfer case or a PTO, it has two transmissions. There is a conventional transmission on the back of the engine that will send majority of the power out back, and it gets about 85-90% of the engine's torque. And then there will be a second gearbox on the front of the engine being driven off of the front of the crankshaft that will get 10 to 15% of the engine's torque based off of a computer controlled shift strategy. That again is going to be an all-wheel drive system, not a four-wheel drive system, so it's not going to be selected by the driver. Now, our low range again is going to be selected either through a button or through a shifter, and is almost always going to be indicative of a four-wheel drive system. To our all-wheel drive system, like what's cut apart here, we will not have a low range option. It's going to just go straight out to the back axle. Now, it depends on the low range, but we can have low ranges get extremely low, and it can make the vehicle undrivable. And again, those four-wheel drive options, to where we're only going at very slow speed. Now, in some all-wheel drive applications, we won't engage the rear axle. We won't have a transfer case or a PTO. Instead, what we're going to have is a viscous coupling. So like the Nissan Skyline use these, the GTRs and whatnot, not the R35, but everything below it, the 34 and back, utilize a viscous coupling. Now, what this is a multi-disc, multi-lined clutch pack that is sealed in a kind of a very viscous material that gets thicker with heat. Under light acceleration or under low torque applications, the clutches will slip and will only engage power to the rear axle. But once we get a certain amount of slippage of the clutch discs, it heats the fluid up to where the fluid almost becomes solid. It locks the clutch discs together, and then it's able to transfer torque to the front axle then at that point. And it won't uncouple until the fluid cools down and becomes more viscous again, and it then unlocks itself. There's a lot of vehicles that do have these viscous couplings. We tend to see it in more automotive applications, not truck applications or SUV applications, but we do see viscous couplers quite a bit. The key note with these is they are not serviceable. They're not rebuildable. Usually, when they do go out, there's nothing internal that can be salvaged. That's why they're all replaced as a unit. Now, inside of our transfer case, if we have a selectable differential, we can have a couple different traction aids inside of that to lock the front and to the rear. The point of the differential is to allow a little bit of slip or movement difference between the front and rear axle when going around corners. But in some situations, if you're in really, really thick mud, you're going to want to lock it. In some cases, we can have an electromagnet lock, so it's an electronic locking center differential. But in other cases, we can have mechanical gears or a torsion style. This uses gears that bind on themselves and lock the front and rear drive shafts together. And they can be selected or deselected based off of that, but they are mechanical use. So when they start to detect slip or one axle spinning faster than than the other axle, then it will bind the gears up and it will send more torque to the axle that's not bound up and to get it moving. We can also have a limited slip style clutch, which is going to have friction lined plates that again will bind on themselves and allow for some slippage, but then also allow for traction at the same point. Transfer cases, if they are manually shifted, are not going to be synchronized. We are going to move the shift fork manually with a lever or with a rod, and that will engage or disengage the transfer case from too high to four low, or even into neutral. When we use this shifter, oftentimes if we're shifting it into a lock situation, we're usually having to shift it into four low and then hitting a button or a solenoid to engage that lock. In some situations, the shifter gets moved up or gets pushed down to engage that locking mechanism as well. You can see the lock mechanism here on this shift fork, where there actually is like a set of teeth that are going to engage into that drive assembly when the shifter is selected correctly. The other thing that we can have on older vehicles is it can be vacuum operated. Now, these vacuum switches are notoriously unreliable. They any type of vacuum leak or anything with the engine running poorly can cause it to have issues. So we don't see vacuum operated systems anymore, only because of their really appalling reliability rate. As stated before, when we shift a transfer case into four-wheel drive, it doesn't necessarily mean that we're sending torque to the front axle. Actually, selecting four-wheel drive usually will also require us to go through and lock the front differential axle shafts or the hubs. First, let's talk about how we're going to engage the transfer case. We can either do it through, again, a mechanical lever, which is either going to move a cable or a series of rods. You can use a vacuum modulator, which again, we talked about in the last slide, has kind of gone away because of its really poor reliability rate. And then most often it's going to be electronically done now with a switch. And then it's also too with the computer, we'll have a rotary switch that will select a drivetrain mode. Our shifter for our mechanical linkage is going to be non-synchronized. So we do need to make sure that we are properly following the instructions on shifting it into four-wheel drive. Usually, this is going to have the vehicle moving. So you're going to want to be below 3 miles per hour. Take the transmission either out of gear if it's a manual or put it into neutral if it's an automatic. Then with light pressure, pull up or move the shifter into into the transfer case position. That will then engage that next speed. You put it back in drive and you are now in four-wheel drive, and it should have a light illuminated on the dash. Now, if it has locking hubs, you would need to go out and you would need to lock those. Most vehicles now, though, however, are going to have an automatic way of doing that. Vacuum switched methods would have a switch that once it sees the transfer case is shifted from two-wheel drive to four-wheel drive, it would automatically send engine vacuum down to the axle disconnect. A lot of electric systems, it will go straight to an electric servo now. These systems are by far the most reliable and the most abundant on four-wheel drive vehicles that are sold now. When I say now, I mean within the last like 25 years. So once you hit that transfer case, the vehicle knows, oh, hey, the driver wants to go into four high and or four low. As long as the speed is correct and we don't have any load on anything, we can use a quick little motor or a solenoid to engage the axle. Why we want the axle disengaged is again for that reasoning of we don't want to have the wheels locked when we're turning left or turning right, binding up, causing the vehicle to hop and lose traction on hard packed surfaces. Our computer controlled system, again, will do this all automatically and it will look at the proper parameters. One of the things to note when you are using a computer controlled transfer case system is if the shifter or if the indication on the cluster is blinking, that means it's in the process of shifting. Now, if it doesn't do it within about 10 seconds, that's usually one of the parameters that the operator has to be within is not being met and it will not shift it. It is important to remember that these vehicles will try to protect themselves from getting wrecked. So we want to make sure that we're not overdoing it in that case. Now let's move to talking about the drive shafts really quick. Now the drive shafts in the rear of the vehicle is going to be very similar to what we're going to have in the front on most four-wheel drive vehicles. Difference though, however, is usually on most four-wheel drive vehicles, the back drive shaft will be what's known as a slip yoke. We can't have that on the front axle, so we're going to have what's called a collapsible slip inside of the drive shaft itself. So the photo there on the left, you can see rubber bellows in the middle of that drive shaft right after the U-joint, and that is going to be for the slip portion of it. What I mean by that is that as the suspension goes up and down in travel, it will then collapse the drive shaft down a little bit or expand it out if we're going in full rebound to allow for the drive shaft to stay in place. We can have to where the joints of the drive shafts are operating at pretty extreme angles. Some manufacturers will employ different types of joints. They used to employ what was called a double cardian joint. That's what's photoed on the left. That is a combination of two cross-style U-joints with a spherical ball bearing in the middle, and it is a single large ball that allows it to pivot, and it can operate at pretty aggressive angles. The problem is that it's very heavy, and we do have a lot of parasitic power loss due to having to turn that joint. We also, too, anytime we have U-joints, they're not turning equally. They're speeding up and slowing down and speeding up and slowing down, and we kind of have a sine wave arc with the operation of that. That can cause a vibration to be felt through the cabin of the vehicle. What a lot of manufacturers are going to is they are going to a Replica style CV joint for the U joint, and what it is it is a set of roller bearings. Usually, it's 6 that are going to allow for smooth pivoting and operation of the joint. Now, we won't have any ability to extend out on either of these joints. We will have to have some sort of slip, but it operates with a lot smoother operation than what we will have with the double cardian at the same style of angle in terms of operational angle that we can have. Now, our front drive axle is going to have the ability to turn left and right as well as go up and down with suspension. So we can either have a U joint on the end, like what we have on most solid axle front vehicles, or we can have a CV joint, very similar to what we were just talking about. The other thing that we might have on the front axle is an axle lock. So, as brought up with the computer controlled or the vacuum controlled four-wheel drive systems, on some mechanical systems, you actually have to get out of the vehicle and lock the hubs. So, what typically you would do is before you start to go off road, you would pull over, you would then get out of the vehicle, and you would move the hub assembly from free hub to locking hub. And you can see on our ASIN hubs here, it's clear that you're going clockwise for locking and counterclockwise for unlocking. You would then get in your vehicle and you would drive down the trail. And then when you would engage four-wheel drive, either high or low, you would be able to have power going to the front and rear axle equally. And then when you were done driving and you were ready to go on the pavement, you would pull over again, have it in two-wheel drive, flip the lever from lock to free, and then you would be able to drive on the hard pack surface again. In some cases, that can be electrically done, but we're starting to see these locking hubs going away only because there's a lot of componentry that's involved with them. And as shown a couple slides back, using one of those motor disconnects is a lot easier. But the way that these work is when you twist the lock into the locking mode, you are pushing a spring against a hub. That hub then goes over a set of splines and locks the axle shaft to the hub assembly. When it's in an unlocked mode, everything is free spinning and the axle shaft just kind of turns on its own. But when you lock it into place, that spring pressure pushes that splined hub assembly over the axle shaft, locking it to the hub and now allowing for the engine torque to go to that wheel. I don't know. Automatically locking hubs are going to use a computer controlled system to be able to lock them. They're going to either use a small air pump and they're going to be pneumatic, or more often than not, they're going to use a servo actuation and will lock them appropriately. Now, one of the things that you can double check to make sure that either design of locking hub is working is a quick test as if you place it in four-wheel drive on hard pavement, but you have the hubs unlocked, you should be able to still steer it normally. If you put the hubs in a lock position, you will feel the steering wheel kind of fight back at you. And the construction of them is very similar. The one key thing is uh, spring tension and getting the right shims is going to be important. I personally don't really like rebuilding these. Everything gets really dirty. It's really hard to see anything, and you got to have everything in the exact right order and indexed correctly for it to work. Now, we're going to spend a little bit of time talking about Subaru all-wheel drive systems, not because, I own a Subaru and that's what I want to talk about, but because Subaru's all-wheel drive system is fairly unique in the automotive world. A lot of the other all-wheel drive systems are using very similar technology to themselves as what we've discussed before. But Subaru all-wheel drive systems will operate with a couple different designs. We will have a viscous center diff. We will have active torque splitting if it's available, and sometimes it's selectable by the driver, and then variable torque distribution. So not only the front and rear, but also to the left and right. This allows four-wheel drive application in an all-wheel drive platform, so it will act as a four-wheel drive when necessary. Now, our viscous center clutch will be located inside of the transaxle, as well as our torque splitting center differential. So we will not have a separate PTO or transfer case. It will all be in one unit. The transmission will have the front differential, as well as the rear center diff and the limited slip viscous coupler all in one housing. It will all be computer controlled, and in some cases, we can lock the viscous coupling via a hydraulic pump. But this gives you a cutaway idea of how this transmission is constructed to where we're going to have the normal gear train components located right here. Our front differential is right here. Our center diff is located right here, and then our output out to the rear axle goes right there. So a lot's going on in these transfer cases. Subarus get a lot of flack for not only head gaskets, but also transmission issues. Well, when you look at the transmission, it's expecting to do a lot. In stock applications, as long as the driver is shifting with a degree of talent that is within its operational range, the transaxle will live a really long life. But when it's misused or too much torque is powered through it, we start to get a lot of different fail points with these systems. Now, the other thing that we have the ability to do is to actively torque split front and rear. So that viscous coupling can be an electrohydraulic clutch pack that will allow for us to send more power forward or more power rearward. It's going to look at not only the wheel speed sensors, but also the yaw sensors to determine if the vehicle is sliding. It will take into consideration the driver input via how much throttle input or brake input that is being applied, and also to the input from the steering angle sensor to see how aggressively the driver or the operator of the vehicle is trying to steer one way or the other. We're able to do this and send torque as equal as possible. A lot of these systems are 45% to the front, 55% to the rear. But in some applications, we can limit that, and we'll actually have a switch on the center of our center console there, right behind the shifter, to which we can request that the transaxle select how we're going to be able to have the four-wheel drive or all-wheel drive system react. And that will be corresponding with a limited slip differential when that is the case. There are some systems, Volkswagen has a similar system, but it is more similar to the PTO system that we talked about earlier. That covers a theory of four-wheel drive systems. We will get further into talking about transfer cases and how they're constructed and how we take them apart, as well as differentials individually in the next coming chapters now that we're moving away from the transmissions. But I appreciate you sticking around to the end of the lecture. Hope you found it entertaining and informative, and I will see you in the next one.